Alright, in this one we'll cover number representations, two's complements, and unsigned representation, addition and subtraction. We'll try to implement an ALU. Then we'll also see others like the types and various implementation and optimizations. So later on we cover the floating point arithmetic and multiplication and division algorithms as well. Now you realize that if you have n bits, you actually have 2 raised to the power n bits, possible different combinations, right? And yeah, this is just a notation showing that the least significant bit is the what rightmost bit, and the most significant one is the what leftmost bit. So usually there is no inherent meaning in terms of difference between control signals and an integer value, right? And we'll see more of that later. But we also have two different representations of numbers, at least in computer arithmetic, right? We have the unsigned version and the signed version. The unsigned version is the one we usually know up to this point. Any number you are given, you can, if it is in base 2, just convert it to base 10, right? Usually those ones are unsigned. And they usually have a very long range, right? So usually they have a big range. So for a very a 32 bit unsigned, you have a range of 0 to 2 raised to the power 32 minus 1, right? Remember you're starting from 0. So and for the second type, we have the signed representation. The signed representation is a bit different because this time for the signed representation, we usually want a way to show the sign as part of the number itself, right? So we usually dedicate the first bit for that. We usually dedicate the first bit for. In that case, the maximum size actually reduces. So that's the disadvantage of using sign bit representation, right? Your range reduces. So for example, if you have 64 bits, right, and you're using sign bit representation, the maximum you can represent is this, and this is just like for the 32-bit version. Yes, and this one, right? So these are just the formula to show the maximum you can represent. I don't think they are very much examinable, but there is also a means to convert from a positive number to a negative number. And when we say positive or negative, we are thinking in signed bit representation, right? In unsigned, everything is I think positive, right? Yes, so we are thinking about signed bits of representation. So for example, if you have um 0 0 0, oh no, sorry, I think okay, I think they are just trying to represent these numbers, but let's see a practical example. So it's just saying that if you have six is 0110. In yeah, 6 is 0110. Now I did 0110 because I want to show that what it is positive. When the first bit is 0, it is positive. When the first bit is 1, it is negative. Now to convert this to negative 6, right? So this is positive 6. To convert it to negative 6, all I do is that I will invert all the bits and add 1. So I invert all the bits. So this one is 0, so it becomes 1. This one is 1, it becomes 0. This one is 1, it also becomes 0. And this one is what? 0, it becomes 1. So I've inverted all the bits. Now I'll add 1. So immediately I add 1, then this one becomes equal to 1, 0, 1, 0. Right. Yeah, so this is equal to negative 6. This is equal to negative 6. And that's it. Now, there is, in fact, a shortcut, right? The shortcut is look at the number. Look for the first one. Okay, so this is the first one. Now, immediately you find the first one. Just do this. Draw a boundary and flip the rest. So this is a 1, so it becomes a 0. This is a 0, so it becomes a 1. right? So now you have 1, 0, and the previous 1, 0, 1, 0, right? Yes, and this is faster, so you can get negative 6. Sorry, this is negative 6. Now that's for convention between positive and negative, right? You'll be seeing that a lot, especially when checking for overflows, when checking for um when sign extending numbers, yes, and we'll be seeing that a lot, and it will also help us in our division and multiplication algorithms. So yes, they say two complements makes hardware simpler, right? And representation affects calculations, not the correctness of answer. And would understand this later, but this is just a view to show how using two's complement you can represent like several numbers. So this is positive 2, this is negative 2, this is 0, this is negative 0. Yes, and that's one funny aspect of two's complement, right? Yes, but we'll see it how it will affect the reduction of range and all that. And here they are trying to do a 4-bit unsigned addition, right? So you realize that this is 0011, which is 3 in binary. This is 1010, which is what 10 in binary. Now when you're adding, here's what 1, here's 0, here's 0. Yes, 1 plus 1 is 0 in binary. So remember 1. So 1 plus 0 plus 1. 1 plus 0 plus 0 will give you 1. Then this is 0 plus 1, which is 1. As simple as that. Now, for the same numbers we are adding previously, for the same number we added in this line, we are going to consider it in signed version. Now, realize that when you consider it in signed version, the previous one is still positive 3, right? Because it starts with 0. But the second one is minus 6. Why? Because it starts with 1, right? And you would also appreciate the fact that if you convert this to two's complement version, you get 0110, which is what 6, right? So that's one way we actually see if you are if they tell you that a number is in signed version, right, and it starts with 1, right, then you should know that fine, it is negative. So you should try and think about how to convert it to what if you want to see it in binary in decimal form, then you should convert it to what you should convert it to first to the two's complement form. Yes, before you see the what positive version, you know that oh, then that's negative. So for example, this 0110, if I take the two's complement, which we've already done, I'll get this 1010, sorry. If I take the two's complement version, I'll get 0110, 110, right? Now this is the two's complement version, and this is the same as 6, right? But remember, here it was starting with what 1, right? So since it was starting with 1 means that it was negative. So it means that this one is actually negative 6, right? And that's what you usually do. Now, here, what they're actually doing is that they are trying to add these two numbers. So they are trying to add 3 to minus 6, right? So 1 plus 3 to minus 6, yes. Or they want to do 3 minus 6. Anyhow you see it. So 1 plus 0 is 1. Now 1 plus 1 is what? 0. Carry 1. So there's a carry 1 here. 1 plus 0 is what? 1. And 0 plus 1 is still 1. Now, what they've added is what 1101, which is negative 3, right? So you realize that what they said earlier, that the representation does not affect the correctness of our answer is actually true, and that proves it. Now we come to subtraction. The truth is that in hardware, we don't really have something like a subtractor. There is a subtractor you can build like from a logical circuit, right? But it's actually a waste of time because you realize that addition is partly subtraction if you consider it this way. If I'm adding two numbers, right? For example, a minus b is the same as a plus minus b, right? A minus b is the same as a plus minus b. So why don't I use an adder? till and go and find minus b and come and add it to a, and still I'll get what? A minus b, right? And here they are showing an example, and I think it's quite clear. So the next part is we are trying to build a full adder, right? And it's a gradual step towards it. Now you realize that for a full adder we only need the inputs, right? And to generate the carry out and the what and the thing, right? So the inputs for any other, right, can be 0 or 1. So another circuit can be like this, right? Let's assume it's a full adder. Now, in DSD2, you actually build this from scratch, but let's assume I'm assuming we already have an idea. So this is a carry input, and these are the bits you are adding, right? Bits you're adding. So let's call this bit A, and let's call this bit B, right? Now let's call this the scene, right? So in adding them, A and B can take various values, and C can also take various values, right? And that's what they've generated. Realize that when you add 0 plus 0 plus 0, you get a carry out of 0 and a sum of 0. When you add 0 plus 0 plus 1, you get a carry out of 0 because you not carry anything, but you get a sum of 1. Yes, and you consider that you generate this table. Now, when you generate this table, I mean, digital system design 1, you realize you have something called K-map, right? So you realize that some parts are what's positive for, like some parts are 1, right? For the sum, and some parts are, uh, yeah, some parts are 1 for the what carry out. Now another has two outputs. I didn't show it, but another has two outputs, right? So you can generate a function for the carry out and the sum, right? But here they generated a function for only the carry out because that's what is actually important to us. So the carry out looks something like this, right? And this one you can generate you can find a solution using K-map, right? But maybe I'll add a document containing that later. But I think it's to make this video extra long. So the ALU performs different logic operations, right? And it's actually at the heart of the process. And you realize that the ALU is nothing more than a very complex adder, right? And would see that it's a very big adder. Now there's one type of adder that we'll take note of. You realize that this adder I brought here can only add two bits, right? A and B. Now, what if you want to add 16 bits? Then the idea is simple. Let's stack more adders together, right? And that brings an idea of what? A ripple carry adder. So that's what you see. So they stack the adders together and they feed the last bits A0 and B0 into the adder. Now the carry input is 0 because when you're starting addition is 0. But the carry output of the first one will go into the carry output of the next one. Right? Just like when you have 1 0 1 plus 1 1 0, right? When you are starting this addition from the right hand side, you see you don't use any carry input, right? So you just add it. 1 plus what? 0 is what? 1. Then 0 plus 1 is 1. Now when you're adding this one, you get what? 1 plus 1, which is what? 2, but we don't have 2 in binary. So we'll say what? 0, remember 1, right? And we come and put the overflow here. Yes, so that's what you see. So for example, this one, A0 and B0 is just the first one and the first 0. The second one, A1 and B1 is just what the um this 0 and this one. And it goes on like that. So you realize that um with this stack of adder, when we are asked to generate the carry, the ith carry, right? It's quite simple. From anywhere you are, it's the carry. Remember the carry equation we did previously, this one. So when I want to generate the next carry, then the next carry will just be A and B. So the A and BI plus A and BI or B and CI, right? So what is just saying is that the carry at any point in time, a carry will occur, right? If both of the inputs are 1, right? For example here, or any one of the inputs assuming A, then you have A and the carry in is 1, or B and the carry in is what? Also 1. That's what it's saying, right? Now, from that very same circuit, we can build a subtractor. And a subtractor, like we already said, is not different from an adder. A subtractor is just when you want to subtract two numbers, right? It means that you just have to find the two's complement of the other for of the second number, right? And now that's what this inverter is doing. Remember the two's complement, you just invert the bit and you add 1. So this one will invert the bits. This inverted you will invert the bit and add 1, and that would do the two's complement operation for you, right? So this one will compute B minus A. Now we realize that, oh, this circuit here is actually not much of a problem. We can combine both an adder and a subtractor at the same time, right? And it brings us to this circuit. So this circuit, it's doing the same thing as the previous circuit above, but it has an enhancement, right? So instead of putting an inverter at A, we want to say now, let's put an XOR gate here, right? So when we put an XOR gate, the XOR gate is such that when one of its input is fixed to 1, it will invert it, the output will be the inverted of the second input, right? So for example, when you have A XOR 1, let me use this one to represent XOR. A XOR 1, this one will give you A bar, right? Yes, and A bar is the what? It's more or less the complement, not completely a complement. Yes, it's the one's complement of it, right? So, for example, for this circuit, if you want to do subtraction with this circuit, right? All what we do is that we'll set the carry input for the first adder to what? 1. Now, immediately we do that, we realize that all these XOR gates now have been fixed to what? 1, right? They have one input tied to 1, which means that they'll invert the other input and give it as the output, right? That's what the XOR gate will do. And here will be what? Here will also be the carry input. So it is like it will invert one of the numbers and to add 1, right? And that's the two's complement we're already doing. Yes. And now when you do that, you get the difference, right? As the answer for the down. So that's basically it. Now we wish to build kind of an ALU, right? But we want to start from a 4-bit adder, right? So we realize that changing what goes into A and B and C, the carry input, can change the other output, right? Realize that the same circuit we use for addition, we could have used it for subtraction by just changing what the carry input. So the whole point is that then here's the signal. So here the signal sub and some other XOR gates alter the other inputs. When sub is equal to 0, the other inputs A, B, and C in Y, A, B, C, I, R, Y, X in 0. So the other produces X plus Y plus 0. Now when sub is equal to 1, yeah, and you have that. So let me explain that one. So what it's saying is that here, remember the very circuit we have from above, right? Now here they've intentionally put all the full adders in a box, right? And now they've come to give you this circuit, right? So that full adders in the box is that this part. Now this is the XOR gate which was there previously. So previously we had B, previously we had A, and this XOR gate was also there. Now you realize that when you tie this carry input, right? So this sub now is actually the carry input, right? The carry input which was used as an input that is now used just as a signal here. And like the earlier slide said, there's no difference between a signal and what a number in computing terms. So here the carry input is this sub, right? Now when the carry input is 1, yes, you perform subtraction. That's what you see here, right? So you realize that you come and invert the A, so you be doing what X plus Y plus Y prime plus 1, and Y prime plus 1 is the same as minus Y, right? And when you don't invert, that is when sub is 0, then you just be doing X plus Y, right? Now we want to abstract it more. we want to build an ALU actually. We just don't want to build an adder subtractor, right? So we want to go ahead further. So we are thinking of fine. Let's put the XOR gate in a box, right? And here we are. So the XOR gates here, those stack of XOR gates here, you put them in a box, right? So it says by the same approach, you can use another to compute other function as well, right? Now figure out where the functions are needed and then put in the logic box. Okay, so we understand that. Now we are trying to alter our inputs, right, to see the various output we'll get. So it says, how can we produce an increment function? That is, supposing we have an ALU instruction. The ALU instruction is just to increment something by one. How can we do that? It's simple. From our very same adder, right, we'll set one of the inputs to 0. Then the element we want to increase, here we are going to take, we'll maintain it, right? Then we'll set the carry input to 1. At the end of the day, we'll just be doing what? That element plus 1. Now, what about if you want to just increment, if you want to decrement something by 1? That one is also simple. We set one of the inputs towards ones, right? And ones, all ones in signed representation means -1. Now we'll maintain the other element which you want to decrease. And we'll set the carry input to 0. Now this one will do what? X minus 1. Now what about we have something they all you, but maybe we want something to move from one register to another. That is also simple. We just set the input to 0. We set the carry input to 0, right? And we leave the elements we want to transfer, right? And here I know there's a bit of a confusion, like we are using y's and x, but it's actually the same thing. The y's are actually the actual inputs that will come in, right? And the a's are the inputs that will get to the other at the end of the day, right? So don't be confused. So the transfer and increment operation have the same A and only differ in the CI inputs. That's what you realize. So the transfer, this is the transfer operation, right? This is the transfer operation where you set what B to X. Now this is the increment operation where you set X you set G into X plus 1, right? You realize that they have the same A, right? They have the same A and the same B, but just different carry inputs. So the other examples, right, where these operations have similar elements, but we'll be seeing them later. So we can draw a table of all the arithmetic functions, right, that our ALU can perform, right? Now we are just assuming, right? We are just assuming that we have an ALU and we can select the function it can perform, right? So that denotes the concept of kind of a multiplexer in there somewhere, right? We don't know yet. So we are assuming that the select inputs are what? S2, S1, S0. Now don't be confused with these S's and these S's, right? These S's are different from the S's here, right? Now we assume that when you have all zeros. We want, like we are building an ALU, right? And we are assuming that fine. We want when you input 0, the ALU should just transfer. It should not add anything to it. It should just what you input should just come at the output. Now when you input 001, the ALU should increment by 1. And that's what you have. So that's a bunch of functions, right? We wish for the ALU to implement. Now we realize that at the end of the day, we have 8 different operations that we wish for the ALU to implement. But then in the building of the ALU, we have to reduce it so that we can draw the logic gate from it, right? So you realize that from here, right? From here, right? Sometimes you just watch and you realize few things. From here, realize that anytime S0 is 0, right? There is nothing to add to X, which means it's plus 0. Anytime S0 is 1, realize that there is something to add to what X, which is what 1. 0, there's nothing. 1, there is 1 here, right? So we can conclude that fine. Then the carry input, right, will be S0. As simple as that. So it means that at the end of the day, yes, I think this one is explaining the diagram further. So at the end of the day, we can remove S0 from it, right? And that's it. That's removing. So when you remove S0 from it, then you'll be left with what? S2 and S1. Now, another thing that we should take note of is that some of the inputs don't actually change between levels, right? So for example, for the very first box, you realize that the A is always zero. For the very second box, you realize that what um Y is like the correct Y. For the third box, Y is what Y bar. And for the fourth box, what we always get what the input A as what once. So we can come up with a more simplified circuit saying that, oh, since we are removing n0 from it, right? And we don't even need 8 states. We just need what? 4 states, right? So, and in each of the 4 states, realize that at state 00, A must be 0. At state 01, Y must be 1. And at state 10, Y must be what? The bar. 1, A must be what? All ones. So that's the concept, right? That's the concept. And remember, y and y bar are assumed to be 4 bits, right? Yes, they can't write y, so they are just saying there's the variable y, and that's the concept. Now, if you take a look at the table, you realize that no, there is something more we could do, right? And that which we could do is that we could assume that why not let y be part of the variables in consideration, right? So we move y from just the side of the table, then we put it as part of a variable because it will be changing, right? You see these ones are constant, 0, 0, 0, 1, 1, 1, they are constants, right? So we move y as part of the variables which will be changing, right? So we realize that for the first part, right, either y is 0 or 1, ai will always be 0. Either y is so for the second line, right, which we have where we have s2 and s1 as 0 1, when y is 0 or 1, you realize that if y is 0, right, ai will be 0 because remember here we put the correct y. If y is 1, ai will be 1 because remember we put the correct y. Now for the third part where we have 1 0, right, you realize that the a we have to put here is what y prime. So when we realize that when y is equal to 0, the a we have to put here is what 1, and when y is equal to 1, the a we have to put here is what 0. So this is just by extension what this same table which we have reduced, right? We are trying to eliminate the variable y, right? And anywhere y affects, then it will affect in the other table. And that's basically it, right? That's just an extension. So realize that no, at the end of the day, then we can build the ALU because we have everything we need, right? We have our input and we have the outputs. Now, how you do this is that you have to consider minimizing the circuit, right? And that's what we use schema. So there, here's just a schema representation of the circuit, right? And now, if it's quite complex to understand this diagram, you can use the real schema out. Draw the real schema bar. It's actually the same thing. It's the same concept from the came up. So you realize that at the end of the day, we'll get these circuits. We'll get these circuits as the final answer. Now, like I was saying, you realize that this circuit is very, very similar to a multiplexer, right? This is like a multiplexer, and these are like the select lines. And that's essentially what we set out to build. We try to build an ALU which can perform different functions, and by using the select lines, we can choose the function we want, right? So that's basically that. So the next part is actually bitwise operations. I think these ones are doable, and we have an AND circuit and an OR and various gates, right? Yeah. So at the end of the day, this is more of reading, and the last part is defining a logic circuit. So just like we went through to define an adder and a subtractor, a transfer and a decrement by one and a increment by one, we can actually implement logic circuits in hardware, right? And it's actually the same methodology. So at the end of the day, these are some of the logic circuits we can represent in hardware, right? And you realize that we can use just like we use multiplexers to select for the different operations in the other subtractor, we can also use the multiplexers here, right? So now you combine these two together and you get a complete ALU. right? Which can do addition, subtraction, and also logic operation. Yeah, so that's what the last slide is saying. And you realize that we have a whole table, right? So when you combine the other subtractor and the logic circuit we just built, you can be able to implement a whole range of functions, right? So now you realize that anytime you realize you see an ALU control signal, know that it is just um, a signal which will select a particular multiplexer, which would do an operation on one of the digits, and it will implement the needed operation. When you stack them up together, you get something like this. Now you can get a more complex form of an ALU, right? And that is like the ALU we built was for a 4-bit ALU, right? Now sometimes you may require more than 4 bits, maybe 16, 8, 12, 32, right? But you don't have to go through the whole process again, right? You can just go by stacking them, and that's what this part is saying. And the next part is about overflows. So realize that with n bit, we have two raised to the power n combinations as already prepared, unsigned. Yes, and you realize that they range for unsigned and for signed. Now, realize that in unsigned addition, we don't have any problem, right? When we add two numbers, we can just get the results, right? You don't have to worry about um, whether the number is positive or negative, right? But there's one thing you have to worry about, and we call it an overflow. Maybe our hardware may not support the overflow, right? So see an example. An example is you're adding these two 3-bit numbers, 5 and 6. 5 is 101, 6 is 110. Now when you add, you get, I think, you get this one, you get 11, right? Now, if your hardware supports only 3 bits, you will come and get 3, right? Instead of 11. And that's bad. So, realize that the carry out is what we use from the MSB, right? So we'll see how to detect overflows more later. Now, when you are dealing with unsigned, right, then the situation changes a bit. So this one is adding -1 to another -1, and what you get is what -2, right? Now realize that in unsigned, just like in signed, the number of zeros in front of the digits doesn't mean anything, right? It's still the same number. In unsigned, the number of zeros doesn't on in front of the digit doesn't mean anything, and the number of ones in front of the digit doesn't mean anything. So what I'm trying to say, when you have 1 1 0 in unsigned, it is different from when you have 1 1 1 0. However, both of them, um, if you are using even different hardware architecture like 4 bits or 3 bits, both of them will be like the same number kind of thing, right? Would see more later, but that's it for overflows. And we are about to look at when and where overflow is not possible. So when you have two positive numbers, right, overflows is not possible. When you have two positive numbers, sorry, overflow is possible. So P1 and P2 are positive numbers, and N1 and N2 are negative numbers. So that's what the P1 P2 greater than 0 is saying. Now it's saying that when you have P1 and P1 plus P2, overflow is possible. When you have P1 plus N1, where P1 is positive, N1 is negative, overflow is not possible. So when you add a positive and a negative number, you cannot get an overflow. When you add a negative and a positive number, you cannot get an overflow. When you add two negative numbers, sometimes you can get an overflow. So that's what it's saying. So what this slide is trying to mean is that just checking the signs is not a sufficient way of confirming an overflow. So a very typical example is here. We're adding 2 plus 5, right? And we are trying to use a little bit hardware. So you realize that we have 0 1 0 and 0 1 1. Now after adding, we get 1 0 1. Now, typically this is correct in unsigned, but in signed version it is wrong. In unsigned, 1 0 1 is 5, and yeah, we are okay. But in signed version, 1 0 1 is -3. How can we add two negative numbers, two positive numbers, and get a negative number? That's That's because of the overflow which occurred, right? So unsigned, unsigned, you realize that when you add two positive numbers and you get a negative number, right? And it means your an overflow occurred. Now we are trying to also add two negative numbers, so -1 and -4. And realize that at the end of the addition, we get what 0, 1, 1. Now that might be that's an error, right? You see, there is supposed to be kind of a one here, right? But the hardware is 3 bits, right? So we are getting a positive number. Remember, the first bit is 0, so it's positive. Now this is also a type of overflow, right? So whether when you're adding two positive numbers and you get a negative answer, or you're adding two negative numbers and you get a positive answer, those are signs of overflow, right? So we try to bring up an equation to detect an overflow, right? And we are saying that here is how an overflow occurs. When the solution, so assuming you are in a 3-bit architecture, right? So when the um, third bit and the complement of the third bit of the first operand and the complement of the third bit of the second operand, right? When this one gives you a 1, it means overflow occurred, or the vice versa. So let me explain. So let's use this. Okay, let's use this very same question, right, to answer it. So for this question, right, this one will be our A, this one will be our B, right, and this one will be our F, because F is what? The sum. Now you realize that F2, F2 means the this third bit, right? So 0, 1, 2, right? We start counting from 0. So the third bit, right? So realize that F2 is 1, right? So 1, and now realize that A2, right? A2 is also the third bit. So A2 is what? 0. So 1 and A2 is 0, but the inverse of 1 is what? 0 is what? 1, right? So 1 and 1. Then B2 is 0, but the inverse of B2 is what? Also 1, right? So when this solution gives you an answer of what? 1, yeah, so 1 and 1 and 1 is 1, right? Gives you an answer of 1, then it means that an overflow occurred. And that's what this equation is trying to do. It's trying to create an overflow. Now the vices another part, or this one also holds true. So it's either that one holds true or this one also holds true. Now you realize that for this question, this one will become 0, right? Here will become 0, because when you do minus of f2, you get 0, and 0 and anything is 0, so here becomes 0. But remember that the first side is 1, right? So 1 or 0 is what? 1, and it means that overflow occurs. Now better still, so better still means that listen, we are trying to generalize this, right? So we are trying to generalize this and say that fine, no matter what you are doing, at the end of the day you get an overflow if the sum bits, right? So the sum bits, if you find the complement of the sum bit, like the very last number of the sum, yes, you find the complement and end them, and you end it with the overflow and the solution, the sum answers first bit, or you do this one and you get a 1. This operation, you get a 1. The then it means an overflow occurred. So it's quite simple. So for the very same question, we can do this operation again, right? So for this same question, we can realize that our SF, right? Our SF is what? 1, right? Our SA is 0, but they said SA bar, so it means that one to be 1, fine. And our SB is 0, but they say SB bar, so SB bar will also be 1. So this one will give us 1. Right? So we don't even need to check for this one, or anything is 1. So it means that this one an overflow, okay. Yes, and that's basically it for detecting overflow. Now there's more literature on detecting overflow, saying the overflow occurs if A minus on A minus B if the signs are the same. Then when you're subtracting negative from when you're subtracting a negative number, when you're subtracting a positive number from a negative number, you get a negative result, right? If you don't get a negative result, it means that overflow occurs. Now, when you're subtracting a negative number from a positive number, you should get a positive result. If you don't get a positive result, it means that an overflow occurred. Mm, more reading on that. Yes, so that is that.